All right, so I hope you have had some time to work on this, and I promised I will show you why um, the old approach is not going to work very well. It will work, but it'll take you a lot of time to solve this problem. And here's why. In old way, what you have to do is to find, FDR, right? By finding, what do you have to do? You find 0 to 2 pi, and you have to find f written in terms of t, and then multiply the dot this with r prime and the r, right? I mean dt. Okay, so that's what you have to do. Now, r is not too bad. In fact, r prime is really easy to calculate, which is negative 3 sine t, comma, 3 cosine t. That's not too bad. Now, f is rather complicated because y cubed turns out to be 27 sine cubed t. Remember, this is my x and this is my y, right? And so that's what y cubed is. Now, x squared is 9 cosine square t plus 3 times 3 cosine t, that's x, and then y squared would be 9 sine square t. And so f is 27 sine cubed t. Don't worry, I'm not going to finish this approach. But 9 cosine square t plus, then what do you have here? You have 3 times 3 times 9. That's 81 cosine t sine square t. Okay, that's my vector value f restricted on this circle. And remember, r prime was this thing here. So f dot r prime, this is what you will be integrating, will be negative 81 sine, and you have sine t here and sine cubed here. So that's sine to the fourth t. And then plus, now you have to multiply this by this expression. That's 27 cosine cubed t plus 243 cosine square cosine square t sine square t. And then you get to integrate this. Now, if you want to, if you're bored because you have nothing else to do, that's okay. You can go ahead and do this, all right? But it's really hard to integrate this, and there are ways to integrate this. You can look up in the table of integration, or you can try to figure out what the integrals or the antiderivatives of sine fourth is, and cosine third, and cosine square times sine square. And the answer will be possible, but that is a lot of work. And that's why I try to tell you that you should try to use Green's theorem to do this. Okay, so what do you need in Green's theorem? Okay, and it may help you for the first few problems when you do this to just go ahead and write down the statement of Green's theorem. You are asked to find the circulation or work integral, which is the integral over C of FDR, which is what? Double integral over the region R, which in this case is the interior of that circle of radius 3. And what's the integrand? Quicks minus pay. Okay, so if you remember that, I think it may help you. And naturally, you may be interested in using the polar coordinates, right? Because R is a circular region. All right, so let's go ahead and try to figure out Qx minus Py. Do I have my thing here? All right, so I don't have this. Let me go ahead and write F again, just for, to make it easier. Y cubed x squared plus 3xy squared. That was my vector field F, capital F. Okay, so this is the P, this is the Q part, and Qx is 2x plus 3y squared. And then Qy is, okay, I have to subtract this. Py is 3y squared. And of course, these things cancel. This just becomes 2x. So all I really need is this, the double integral over the region R of 2x and then dA. Now I can try to define that circular region in terms of, x and y, but it's probably easier if you go from 0 to 2 pi and then 0 to 3 because the radius was 3. And I can't use x anymore, right? If I use polar coordinates. But that's okay because, I mean, x is easy. 2r cosine theta. Okay, so this is what I have to integrate, 2r cosine theta. And now what do I have for dA? Remember, you have to have that extra letter r for dA, and then dr d theta. So in a sense, you are integrating 2r squared. That's the first thing you will be integrating, okay? But that's still not too bad because that's just 2/3 r cubed, and then you go from 0 to 3, and you still have cosine of theta d theta to integrate. But this whole part is just going to be constant, right? What is that? It's 2/3, and then you have 27 minus 0, and then you have cosine theta to theta. Now you can, work this. This is easy. That's 18, whatever, right? But look at what happens here. What do you get when you integrate cosine or sine or any, any trigonometric function of period 2 pi? Well, you actually get 0, right? I mean, if you really want to, you can write this as sine of theta going from 0 to 2 pi, but sine of 2 pi is 0, sine of theta is 0. So this turns out to be 0, okay? And you may have noticed as soon as you got this, because you got this very symmetric region R, 2x, this side is positive, this side is negative, they cancel each other, the answer must be 0. So the answer is 0. And if you go with this way, the answer would be 0 also, but it's much more difficult to evaluate. Okay, so that is the power of Green's theorem, and you can do things in a much shorter way. Let me give you another example, and then we will. I'll try to solve this. Actually, I can give you a couple more examples here. Okay. This time, let's do rectangular or square region. All right, so the next question has to do with region R, which is a square. It's a 1x1 square, and the bound, the C is the curve consisting of C1, C2, C3, and C4, which pretty much just surrounds or goes around the region R in a counterclockwise direction. So C is the boundary of the unit square. You can write this as C1 union C2 union C3 union C4. And when I write this 0, 1 cross 0, 1, this is called the Cartesian product of the unit interval 0, 1. And basically, it just means a 1x1 square with every point inside. Now, you have to evaluate this. Now, I haven't used this kind of notation very often yet because, this is not my favorite way to write dx and dy. But when you see a problem like this, oh, by the way, I should have also mentioned this. Let me just go ahead and erase this. Many times, if the curve is a closed curve, and if it bounds a region R, the authors have not just used the integration, the symbol, but use a little circle to show you that this integral is along a closed boundary circle or a closed boundary curve, and so just don't be scared with this little circle that you see on top of the integral symbol, because that really doesn't mean anything except to emphasize that the curve C is closed. Okay, this is not even don't even think it's like a musical notation when something like that. It's it does look like a treble clef, but it's not the same thing. So okay, so so that's the question. Now what are we supposed to do? Well, do you see the vector field that is implicit in this problem? Okay, so you have something dx, something dy, right? So the implication is this is your first part and this is your second part. So your vector field that you are integrating, or you're trying to find the work for, you're trying to find the work done by this vector field along the curve C1, C2, C3, C4, and that is negative y square, comma, xy. Okay, that is the vector field that we are considering. And so you know how you can write this as p dx plus q dy, or pq dotted with dx dy. And so that's all the same thing. And so this pq is actually this. So you need to be able to interpret a question like this, because a lot of times they will just give you what to integrate in this format. And if you're not used to it, you wonder what are they asking for? What does this integral represent? And the answer, it is a work integral, just like this. And this is, it's basically FDR in sort of a strange form, but it is acceptable, and it is often used a form of this vector, the work integral. So you need to just remember that people sometimes write it this way. And your homework will ask you questions in this format. So I want you to know what that means. All right. So with that, what do you have to do in the old way? Okay. What you have to do is what you would have to do is to parameterize each one of these, C1, C2, C3, and C4. And for each edge or each segment, you have to write this in terms of T, which is not too hard. Okay, and then you have to find the integral, and you can do this in along all of four edges, and maybe you should do that in your spare time, and then you can add them. Okay, that's one way of doing this, but the new way is much better, because Green's theorem allows you to do this not in four separate ways and then combining them, but you know that this thing, which what you're trying to calculate, turns out to be, what was it? Qx minus pay. And you can use the rectangular coordinates, because the region R is basically a rectangle. It is a square. Okay, so let's try to figure out what Qx minus Py is. Well, Qx minus Py, remember, this is my P, and this is my Q, right? So this is the P, this is the Q, and so Qx is simply y. And how about Py? This is the P, and so Py is, okay, it's y minus, right? And what Py is negative 2y. And so that turns out to be 3y. Okay, so that's not too bad, is it? And so that's what you have to integrate. And let's go ahead and integrate. How do you integrate over this region R? It's 0, 1, 0, 1. That's really nice, right? And the dA is simply dy dx, or dx dy. It doesn't matter in this case. And so this is 3 over 2 y squared. Okay, and so this is 3 over 2, the integral from 0 to 1 of dx, and that's just 3 over 2. So it is much simpler than trying to do this parameterization of each of the four edges and then evaluating the line integral over each of the four edges. Okay, so I hope that is understandable, and that you got this point so far. I can do a couple more examples, but I think I want to focus on the other part. Remember, I said there is another version of Green's theorem, and so that's what I would like to focus on now. All right, you can take a break now if you want, because I am ready to go into the second aspect of Green's theorem. I will not spend more time on this one. This will be brief, but there's a little trick for this. Okay, now you know what we have been doing is the work, or the flow, or circulation integral. Okay, so how do you find the circulation? That work or circulation is defined as the integral, it's a line integral over the curve C of P dx plus Q dy, right? Remember, I am thinking of F as PQ at this point. And you can write this as the integral. Now, we just learned that in Green's theorem, this is equal to what? Qx minus pay. And I also made a comment, and this will be more apparent when we study the next section, but this part is called the the curl of f. Okay, and so that's what we decided that's what we decided was, well, that's what I stated as Green's theorem. Right now, do you remember if C is like this, we had this tangential component, and then we can also define the normal component. All right, and so what I mentioned back then is that T, if this is dx dy in that order, times dt if you want, yeah, something like this, then n was, do you remember what this was? It was dy comma negative dx. It's 90 degrees turned from the right hand in the right direction. So in other words, if you go from t to n, you turn this 90 direction in the clockwise orientation. That's how you get n, and the order of this vector is dy comma negative dx. All right, so Green's theorem version 2 has to do with, and I should probably use a different color. Maybe I should represent blue as my normal or flux direction, or flux portion of this. So when you are trying to find the flux, which is not work along C, but you remember it's how much of the stuff is going across that curve C, right? And so in the flux situation, the integral for the flux was not P dx q dy, but it's P times dy plus q times negative dx, right? And that's all because the tangential components were dx dy, but the normal components are dy comma negative dx. So this is what we, defined as the flux integral. Now I'm going to switch the order of this because typically it's easier to write dx first and dy next. Okay, now I want you to look at this really carefully. Okay, the Green's theorem, and think of Green's theorem purely in its form. You can apply Green's theorem to this side and come up with a double integral that represents a flux. Okay, now remember, PQ was my original vector field, okay, and they appear here and here. Now what we have is this. I have a different vector field, basically, negative q comma p. And so what do you think the right-hand side of Green's theorem is? If this is my vector field, look at what happens here. Over here, if you look really careful, the first term was the partial of this thing with respect to x. Over here, this thing that I'm talking about is actually called p, right? So over here, you take q and take the derivative of that with respect to x, and that's what you got here. That's the first thing I write here. But over here, so what happened here is this was the second component I saw, and take the derivative of the second component with respect to x. If I do the same thing here, that's what you get. It's going to be px. Okay. Now this minus sign, I will just go ahead and put minus. And then what is the last thing you write? That would be the first component and differentiate it with respect to y. My first component is this now. So it's minus qy. That's what I have, right? And then you have dA. But watch what happens here. You have the double negative. Like, don't tell nobody that's double negative, right? And so double negative makes it positive. And so here is the flux integral according to Green's theorem. And so this is called the second part of Green's theorem. And this is the flux version of Green's theorem. It says the flux across C defined by, or by the movement described by this vector field F is the double integral of, guess what? Px plus qy dA. Okay, so I hope you understood this because what happens is, over here, see this second part was differentiated with respect to x, and that's the first part, so that, and then for the second, the last part of the double integral, you take what appeared first and differentiate it with respect to y, and that's this, differentiate it with respect to y, and it carries a negative sign, so it becomes positive. All right, so let me summarize what I have. The two two parts of Green's theorem, and I think it'll be clear if I just summarize both of these. All right, so two versions of Green's theorem. We, in both cases, assume that the region R is surrounded by or bounded by the closed loop C, the simple closed curve C. And we assume that a vector field F, which is PQ, is given. To find the work or circulation, remember we do this, it's FDR, which is the double, and Green's theorem, the first version says it's equal to the double integral over the region R of Quicks minus Pei. The flux is not FDR, right? So this will be, as I said, it's a negative Q dx plus P dy. You don't have to memorize that part, but it's going to be the double integral over the region R of Px plus Qy. So this is maybe even easier to remember because PQ is the original, order, and then XY is the original order. All right, and so this is how you get the second part of Green's theorem. So again, remember, Green's theorem has two parts, okay? The first part is the work and circulation. This is the most basic, the fundamental version. And I mentioned that this part is called the curl of F. Again, this is something we will explore in the next section. On the other hand, this new integrand, which we obtained by applying the first part of Green's theorem to the flux formula. And so this is called the divergence of F. Divergence of F. All right, and just so you know what's coming up, it turns out if you extend one to the a three-dimensional space, it's called Stokes' theorem. If you extend this flux to the higher dimension, the three-dimensional space, then you get the divergence theorem. So both of these named theorems, which will be coming in the next couple of days and couple of sections, will be an application. Each of them will be an application of Green's theorem. Okay, so that's how they are connected with each other. I'll revisit the relationship between all of these theorems again once you finish with this. You are finished with this. Okay, so that is the divergence. Now let me give you a problem, and then I will give you a chance to a few minutes to solve those two problems, or problem with two parts actually, and then let you think about this, and then the answer will be in the third part of this video lecture for this section. All right, let F be, let's make it simple, xy, okay? And C is this curve, which is a unit circle. All right, you know what unit circle is. It's the circle of radius 1 centered at the origin, and the most common parameterization of that is cosine t sine t as t goes from 0 to 2 pi. Right, no problem here, right? So what you have here is the following. Basically, what I'm going to ask you to do, right? I'll go ahead and I'll go ahead and make a little comment about this actually. All right. So this is what we have. Your circle, it's not C1, it's just C. Okay. The curve is C, the unit circle, and the vector field xy is the given vector field. All right. I want you to find the work done by F along C and the flux of F across C. And when I say flux, the flux, I am assuming that we're talking about the flux from the inside coming out, okay? And that's consistent with the orientation of the boundary and so on. But before you go any further than on this one, I want you to think about what this vector field xy looks like. Right? At 1, 0, the vector is 1, 0. At 0, 1, the vector is 0, 1. Okay, at this point, which is what? Square root of 2 over 2, comma, square root of 2 over 2, the F is the same. So you can tell that this is a vector field. This is the vector field that goes away from the origin at any single point. Okay, basically at the value of the vector field at any single point is an arrow that goes away from the point. Okay, and it is perpendicular to the unit circle at every single point of the unit circle. That may tell you what the work is. You may be able to figure this out without even calculating it, okay? And the flux is going to be definitely positive because at every single point, the fluid or whatever the energy or whatever is coming out from inside the circle. All right. So I want you to use not the, well, you can use the parametrization and you can do this in old fashioned way for both of these, right? But try to use Green's theorem and come up with the answer. In fact, you can even use the fundamental theorem of line integrals. All right. So when you spend some time figuring this out, you can come back to the next part of this video. Okay, so the quickest way to do both is to use Green's theorem. All right, so remember work. Oh, yeah, so let's see. I should say P is X here, Q is Y. Um, all right, so the work integral is the double integral over the region R, and region R is the interior of this circle, unit circle. And so remember what work is. It's the integral of FDR, which is the double integral of Quix minus pay. Okay, what's P? So Py is 0, Qx is 0. Okay, so this is actually just 0. Now you could have expected this because remember the work done is the tangential components added together at each point. So at each point we ask, as you go along C in a circular motion, what is the tangential component of the vector field F? And the answer is 0 because at every single point F is perpendicular to the tangent line to the points on C, right? So in other words, F is not doing any work at all as you go around this C. And basically, it's like you're trying to, go around this sail and then the wind is kind of going in this way. It's not pushing you forward or backwards. It's perpendicular. So at every single point, the tangential component of F is 0. If you add up a bunch of 0 as you go around the circle, you get 0. So that's the answer, okay? And I will maybe mention another way of doing this. Maybe two other way of doing this. And then what is the flux? That would be the double integral of this one. Remember, it's px plus qy. Do I have to know this? Yeah, but you will get to know this. I mean, once you do a few problems, you will remember these, okay? The key is if you're just watching this and if you're not doing this on your own, not writing anything down, it's really confusing or it appears to be confusing. But if you actually jump into the water, actually start doing the problems, okay, after a few problems, I think you will get this. It's not that difficult, right? And so this will be what? Well, px is 1 and qy is also 1. So 1 plus 1, that's 2. Okay, now what is 2 times the integral, double integral of dA? Double integral of dA is simply the area, okay? Area of the unit circle, which is, of course, 1 square times pi. It's 2 pi. So it is 2 pi. And what this 2 is telling you is at every point of this unit circle, because F is showing you how much penetration is happening, and it turns out, as you can see, this number is 2. Well, I guess that's not the point. But the point is that you can find the flux at each point. In fact, I may actually do that. But if you integrate it, the net flux or the overall flux in the amount of stuff or the energy flowing out from inside of the circle out to the outside is 2 pi. All right, I will let you, let me show you how to think about this again in the old way without using Green's theorem, okay? So remember RT is cosine comma sine, so R prime is negative sine T cosine T, okay? Now F happens to be xy, which is cosine T sine T, right? Because F is xy. and R was cosine t sine t, which basically means that this was X and this is Y, okay? And so the work integral, remember this is f dr. Now remember, this is if you didn't use Green's theorem. This will be, you remember what this is? It's f dot r prime dt going from 0 to 2 pi. And the reason I'm showing you this is because this actually illustrates, as you calculate this, it tells you something very important about every single point. What's f comma r prime? Well, you take the dot product of this, okay? And that would be negative sine t cosine t plus sine t cosine t dt. And of course, that's just 0. Okay, and what this is saying is not only is the work integral 0, but at every single point of the circle, the tangential component is 0, which is what I was talking about, right? Right here, the wind F is not doing anything, not pushing you forward or backwards. So if you add 0 2 pi times, basically, you still get 0. Okay. On the other hand, the flux integral is different. Okay, remember what flux integral is? It's not p, it's negative q dx plus p dy, right? And so how do you calculate that? This will be something like this. You can take negative q, p as a new vector, and then dx dy, it's going to be r prime. Okay, so what is negative q? That's so this is this was my, here, let's go ahead and write this. This is the P, and this is the Q that's going back to the original vector field. And so negative Q is negative sine T. Negative Q is, okay, and P is cosine of T. And remember what the R prime was. That's negative sine T, cosine of T, dt. Okay, and so this actually reveals something more, some more information than before. So this is sine square, negative times negative is positive, and then cosine square. And of course, that's 1, right? And so what does this 1 mean? Well, that means that every single point, okay, the amount going from the inside to the outside is 1 amount of energy or the fluid or air or whatever. And so at every single point, the penetration or the single point flux is 1. And because you go around all of these points, the circumference of 2 pi, you just get 2 pi as your total amount of flux. And so that's what you were calculating. Of course, this will take you much longer, I think, than to use Green's theorem. So that is the power, again, of Green's theorem. Okay, so that is pretty much all of the section, except I have one more important thing, and this is a very clever application. I hope what I'm about to say is not confusing. Let me tell you what I am about to tell you. All right, so you'll have a few problems of this nature in your homework, but this last part has to do with how to find areas using Green's theorem. Okay, so let's say you have some sort of a parametrized simple closed curve, like maybe this one. Okay, this is kind of, weird thing here. And C is parameterized by R of T. Okay, and you're trying to find the area of R. How do you find the area of the region? This is kind of ugly. Let's just make it a little more reasonable. Okay, so if a parameterized simple closed curve, basically it's a loop, is given, how do you find the region R inside? All right, and it has to do with a little clever application of Green's theorem. All right, and I'll tell you what you have to do here. What you have to do is to consider let F be this one particular vector field, -2, -1/2 y, 1/2 x. Now, this sounds weird, like what in the world? Okay, but this is something very clever, okay? And you will see how, I don't know who thought about this, but it turns out this will give us in such a nice way how to find the area of a closed a closed region R. Okay, and I'm going to give you one more thing. This is I think it is nice if you understand this ahead of time. You let F be this one particular vector field, and use Green's theorem backwards. Let me tell you what I mean by that. Okay, we are so used to reading from left to right. Green's theorem is basically saying that this integral FDR is the double integral of Qx minus P, right? So that's fine. This time, we are going to find this in terms of this. Okay, sometimes you have to use equations in the backward motion. Okay, I'm sorry, you have to do that, but that's okay. And it is nice, right? So one thing is, let's start with a positive attitude. This is not just one extra thing that you are learning in section 6.4, but it is a clever use of Green's theorem backwards. What do we mean by this? All right, so remember, area. Okay, watch, this is actually pretty, okay? So remember, area is equal to the double integral over the region of dA, right? That's the definition of what area is, actually. All right, so that is, of course, what is the integrand? It's just 1 dA, right? Okay, so here's the pretty part of this. I am, this is my P, and this is my Q, right? All right, so I should have done this earlier, okay? In this case, for this vector field F, and that's why this vector field F is carefully chosen, right? In this case, what is Qx minus P, which is the curl of F? Well, Qx minus P, Q is a 1/2 x, so it's 1/2 minus what's the Py? The partial of P with respect to y is negative 1/2. And so it is actually 1, okay? And that's why I put 1 in here, because it turns out for this very specific vector field, which is cleverly defined by someone, it is Qx minus Py, which is exactly 1, right? Now, this is the right-hand side of Green's theorem. So now I am going to apply Green's theorem going from right to left in this case. This is the line integral over the boundary curve C of FDR. Get that? All right, and of course, you know how to calculate this. This is, let's say, go from A to B of F dot R prime dt, right? And that's something we've done. Let me give you one example and I will quit. All right, so let's talk about, here's one example. Here's the one example I'm going to give in applying Green's theorem to find the area. Okay, so the question would be something like this. Find the area of this ellipse. So you have a semi-major axis, which is 4 units long, and then the semi-minor axis is 3 units long. It's basically a 8 by 6 ellipse, right? And so remember, we've done this before when we used the Jacobian, the UV substitution. And we found that the area is just basically it's AB times pi, where this is your A and this is your B. So the answer is going to be 12 pi. Okay, so we kind of have the formula for this. Remember, a circle is a very specific type of ellipse where A and B are both R, and that's why you have pi times R squared as the area. But using this application of Green's theorem, this is what you can do. Remember, F, in this case, we define this to be negative 1/2 y and 1/2 x. This is the standard vector field in order to calculate the area using Green's theorem. All right. Now, you remember how you parameterize C? Well, C is not a vector. C, you can parameterize as RT is, in this case, it's 4 cosine T, 3 sine T, as T goes from 0 to 2 pi, right? Now, remember, this time I'm using Green's theorem backwards. So I'm going to calculate this and say that is equal to this, which is the area, okay? So what I need is that line integral on the left-hand side of the statement of Green's theorem. So in this case, f will be, remember, this is my x and this is my y. So f is negative 1/2 times 3 sine of t, comma, and then 1/2 times x, which is 4 cosine of t. Let's simplify this. Negative 3 halves sine t, 2 cosine t. This is my vector field f restricted to the points on the ellipse. Now r prime, remember eventually I have to dot these, is negative 4 sine t, 3 cosine t. Okay, so now let's integrate. Let's do f dot r. Let's take the dot product of this. So you get negative 12 over 2, that's 6 sine square t, plus, and then you multiply these two, that's 6 cosine square t, and that's just 6. All right, so the area, according to what we derived up here, is the single integral of f dr over the circle. That's from 0 to 2 pi of 6 dt, and that is 12 pi, as we expected, right? And so that's how you can find the area. It is very clever in the sense that somebody came up with this vector field so that qx minus py is exactly 1, right? And so using the originally the left-hand side of vector, the Green's theorem, that's what you can calculate, and that way you can find the area of the enclosed area, enclosed region C. All right, so I know that this section has also been a rather long section, but I want you to remember to learn, remember that we've learned about 3 things here. Number 1, Green's theorem, the most basic and the fundamental version of it, which says that the integral of FDR is the double integral of Qx minus P dA, right? That's the first one and the most essential one. But if you switch things around, you can get the flux integral as the double integral of Px plus Qy dA, okay? And that Px plus Qy later we will find represents the divergence of that vector field. And finally, a nice and clever way of applying Green's theorem to find the area of an enclosed region R. Okay, you have about 10 questions on your homework. I am sure you're ready for it. One key thing here, this kind of thing may not come natural to you. Okay, this is a very different kind of calculus. It's vector calculus, and so I can't emphasize the importance of actually writing, taking notes, moving your hands as you write and as you think. Okay, because somehow as you write and as you start thinking about what you're writing, that would engage your mind. And as you do your exercises, that's going to really help you understand the material. All right, so I hope you have a great day and have a nice week. Take care. Bye.